So if you're given an equation like f of x equals 2x plus 1, which if you were to graph this function, it would look have a y-intercept of 1 and a slope of 2, so it looks something like this. You can see that it passes the horizontal and vertical line test, right? No matter where you draw a horizontal or vertical line, it hits once. That means it's a function and it's also one-to-one. So in general, as we work these examples, assume that the function is one-to-one. We won't verify it every time. The reason for that is you can only consider inverse functions if the original function is one-to-one or injective. So here's an example. Now this function has an inverse, f inverse of x, and we want to figure out what the general equation for that is. So how do we do it? Well, we use the basic ideas we talked about with inverse functions. Y represents the original function, so I could rewrite this equation as y equals 2x plus 1. But inverse functions swap the input and output, or the x and y, so let's go ahead and swap the x with the y. Replace every y with x, every x with y. The idea is now y, this new y, represents the inverse function. So if we solve for it, we're actually determining the equation for the inverse function. So that's our goal. So to solve for it, subtract 1 and divide by 2. This is the inverse function. So f inverse of x equals x minus 1 over 2. So since this is f inverse is a function of x, notice I've only got x's over here, no y's. So that's very good. Another way to think about this is, what would this machine look like if we actually drew it? So the machine f would look like this. X would go through, it would be multiplied by 2 first, and then you'd add 1, and you'd get the result. So the inverse function, if I were to draw it the opposite direction, needs to undo all of these in the opposite order. So if I send x in, how do I undo plus 1? Well, I subtract 1. And then, how do I undo times 2? I divide by 2. And what comes out? Well, x minus 1 comes out of here, and then divide by 2, and you get x minus 1 over 2, which is the same thing we got there. Now this is a great theoretical approach, but sometimes the functions can get really complicated, so you can't always draw this very nice diagram and just undo the operations in the given order. Let's take one more example to show you what I mean. So how in the world would you draw a picture of this? Well, I don't know. I couldn't draw a machine diagram like I did before. So we can still find the equation for f inverse by replacing f of x with y, changing y to x, and changing all the x's to y. And now our goal is to solve for y, but the problem is I have two of them. And remember, y represents the inverse function now. This new y represents the inverse function. So let's do the obvious thing and get rid of the fraction, multiply both sides by y minus 1, and that allows us to cancel with the denominator here. And over here, let's distribute x. And I still have this problem of having a y here and a y here, so how do I get the y's together? Let's get all the y's on the same side. And let's add the x over here. And now I've got my y's on the same side at least. So how do I solve for y? Well, how do I make two y's into one in this case? Well, I can't actually combine xy and negative y. They're not like terms. I can do the next best thing though and factor out the y. And finally, to get the y by itself now, I can divide both sides by x minus 1, which allows these to cancel. So I have y equals x plus 2 over x minus 1. And remember, this new y is the inverse function. Now something very interesting happened here that I didn't anticipate. The original function is exactly the same as the inverse function. That can happen in some unusual cases. So be really careful with things like that.